It's an honor to be here to recognize the great contributions of Eugene Parker, whose brilliant work revolutionized our understanding of the heliosphere. My name is Rocky Cobb. I'm Dean of the Physical Sciences at the University of Chicago and a professor in the Department of Astronomy and Astrophysics. It's my privilege to welcome our distinguished speakers. Dr. Thomas Zurbuchen is the Associate Administrator for the Science Mission Directorate at NASA headquarters in Washington. Dr. Zurbuchen previously served as Professor of Space Science and Aerospace Engineering at the University of Michigan. His research focused on solar and heliospheric physics. He was also the university's founding director of the Center for Entrepreneurship in the College of Engineering. Dr. Zurbuchen has been involved with several NASA science missions. He earned his PhD and Master of Science degree, both in physics, from the University of Bern in Switzerland. He's received many honors, including the National Science and Technology Council Presidential Early Career Award for Scientists and Engineers in 2004, and a NASA Group Achievement Award in 2006. Dr. Nikki Fox is the project scientist for the Solar Probe Plus. Since 2015, she has served as chief scientist for heliophysics in the Space Research Branch of Johns Hopkins University Applied Physics Laboratory. She was the deputy project scientist for NASA's Van Allen probe mission, which studied the radiation belts that surround Earth. Before joining APL as a research scientist in 1998, she was a National Research Council Fellow at NASA's Goddard Space Flight Center. She earned a PhD in physics from the Imperial College, London. Our next speaker, Eric Isaacs, is the Executive Vice President for Research, Innovation, and National Laboratories at the University of Chicago. In that role, he provides direct oversight of Argonne National Laboratory, Fermilab, the Marine Biological Laboratory, and the university's founding partner relationship with the Giant Magellan Telescope project. His responsibilities include furthering the university's effort in computation, data science, and innovation in Hyde Park, including the Polsky Center for Entrepreneurship and Innovation. He is the Robert A. Millikan Distinguished Service Professor of Physics. He previously served as the university's provost and as director of Argonne National Laboratory. Dr. Isaacs earned a PhD in physics from MIT, and he is a condensed matter physicist whose work focuses on quantum materials. Please join me in giving a warm welcome to Dr. Eric Isaacs.
Thank you, Rocky, for that welcome. And good morning to everybody. And I also want to extend my welcome to Thomas and our partners at NASA. We're really an extraordinary day today. We're here to honor Professor Eugene Parker, who's the University of Chicago Emeritus Professor in Astronomy and Astrophysics. Gene Parker was an assistant professor in the Department of Physics and the Enrico Fermi Institute in 1958 when he predicted the existence of the solar wind. It was a fundamental insight that forever changed the way in which we understood the sun, the heliosphere, and in general interplanetary space. To give you an idea of how transformative this idea was when he first proposed it, until this discovery of the solar wind, this prediction of the solar wind by Professor Parker, scientists regarded the space in between planets outside the heliosphere as essentially a vacuum. So this was really a transformative idea at the time. And really, by and large, this and other projects that Professor Parker led really led to define, let's call it heliophysics and the study of the sun. Now, when the idea first came out, there was a lot of opposition to this idea, what I'd call revolutionary idea. It was quite strong. His first paper, which was submitted to the Astrophysical Journal, was rejected by its two referees. The paper, interestingly enough, was saved by another colleague of ours, Professor Subramanian Chandrasekhar, Chandra, who spent nearly 60 years at the university as a faculty member and who later received, as many of you know, the 1983 Nobel Prize in physics. So Chandra clearly understood that important insights into the nature of the universe, into science in general, were not always warmly welcomed at first. In fact, Chandra himself had been ridiculed when he, a generation earlier, had predicted that massive stars, much more massive than our own sun, could collapse into something he then called black holes. Less than 2 years after the paper that was published, the paper on the solar wind was published, Professor Parker's theory, his prediction was actually confirmed directly by satellite observations of the solar wind. And the rest, of course, is history. Professor Parker later became the Chandrasekhar Distinguished Service Professor, and in 1999, NASA named its flagship mission for X-ray astronomy in honor of Chandrasekhar, whose timely invention ensured that Parker's insight received the public platform that it deserved. So these interconnected relationships between NASA and legendary astrophysicists at the University of Chicago are neither unique nor coincidental. This university has been at the forefront of astronomy for over 220 years, ever since the very first light at the Yerkes Observatory on May 1897. It's been a while. So, with its 40-inch refracting telescope, Yerkes, as many of you know, retained the title of the world's largest telescope for more than a decade. Of course, it's still the world's largest refracting telescope. You can debate the usefulness of that, but it also became the home of the university's Department of Astronomy and Astrophysics early on. And that's where Edwin Hubble was working when he completed his PhD at Yerkes in 1919. And his name lives on in NASA's Hubble Space Telescope, of course, the first major optical telescope to be placed in space. And of course, Hubble is but one of the list of extraordinary University of Chicago astrophysicists. In this short time, 120 years, it is impossible to go through the entire list of what we've done. But I'd like to mention a few. Today, the University of Chicago remains at the cutting edge of discovery in astronomy and astrophysics. We are the leading U.S. collaborator on an international project to deploy a cosmic ray telescope on the International Space Station later this decade, the Extreme Universe Space Observatory, which is funded by a grant from NASA. The university is also a core participant in the South Pole Telescope, which is a powerful tool already in operation, looking at the structures of the cosmic microwave background and searching, for example, for dark energy. We're also the founding partner in the Giant Magellan Telescope in Chile, which will be the world's largest optical telescope when it begins early operations in 2021, and which will produce images that are at least 10 times sharper than what we can do today on Earth. Or by the Hubble Space Telescope in the sky. We're also an organizer of the Pierre Auger Observatory in Argentina, which is a cosmic ray detector, a very large one, roughly the size of the state of Rhode Island. So these exceptional tools of discovery are matched by our outstanding faculty and other university researchers. Our Department of Astronomy and Astrophysics is home to an exceptionally talented faculty who are opening the door to the cosmos for the next generation of astronomers, astrophysicists, and everyone else who is passionate about science and discovery. So, suffice to say, we're very proud to join NASA in honoring Professor Parker for his revolutionary vision of the cosmos, of the sun, the heliosphere, and for his seminal contribution to plasma astrophysics. So we look forward to continuing our exploration of the universe in partnership with NASA and with scientists across the country and around the world. Thank you.
Thank you, Eric. Today's event was almost 60 years in the making. In October of 1958, University of Chicago professor John Simpson convened the Physics of Fields and Particles in Space Committee of the Space Science Board. Right here on campus in 1958, the Space Science Board ultimately advised NASA, the Department of Defense, and the National Science Foundation on aspects of interplanetary probes and space stations, potential problems of manned spaceflight, the exploration of Venus and Mars, and other space-related matters. They also added a list of long-range plans for particularly interesting research. That list included a solar probe to study particles and fields in the vicinity of the sun. Since that first meeting of the Simpson Committee, the solar probe has remained at the top of various National Academy and NASA science policy lists. So it's very appropriate that we're here in Chicago today to honor Eugene Parker, whose groundbreaking work reshaped our vision of the solar system and set this entire endeavor in motion. In the 6 decades since Eugene Parker's discovery of the solar wind, we have made tremendous gains in our knowledge of solar and space physics. Through NASA's missions to space, we have investigated the composition, properties, and structure of the solar wind. We have captured incredibly detailed images of the sun's corona. We have advanced our knowledge in ways that the committee might not have dreamed of. And yet, so many fundamental questions about the solar wind remain unanswered. 6 decades ago, Eugene Parker asked a fundamental question about the structure of the sun's corona. That question led him to predict the existence of the solar wind and permanently transform the way we think of space. Today, we celebrate the profound question that he asked and the brilliance and creativity with which he answered it. But even more importantly, we celebrate the questions that flowed from that first answer, questions that have led us through 6 decades to this historic mission. We look forward to finding answers to those questions through the data that the solar probe will send to us. But even more, we look forward to new questions that will arise from those answers, which will point us to yet more exciting discoveries. Thank you. We would now like to share with you a video about Eugene Parker and the impressive work that has brought us here today.
Well, the sun is the primary puzzle in the universe because it's the one star we can observe in detail, and stars are complicated things. You can't imagine all the strange things that have been discovered in the sun. As a child, I enjoyed very much learning how things work. And when I was in high school, I took the physics course my last year and realized how fascinated I was. When I first stumbled across the mathematics that established the solar wind, it was 1957. I was 30 years old. C over V equals... It's so simple. 4 lines of algebra. In my first 2 or 3 papers on the solar wind does not appear. I talked about solar corpuscular radiation, and then I sort of realized it's a flow of gas. And it sort of hit me, it's the solar wind. When I wrote the first paper, as far as I was concerned, it was open and shut. I remember how upset the referee was that Chandrasekhar, the editor, sent my first paper to, and he said, "This is ridiculous, and before you write a scientific paper, you should at least take the trouble of going to the library and reading up on the subject." No further criticism, no further comment. My response to Chandrasekhar was, well, he couldn't find anything wrong with it. It must be pretty good. I've always looked upon myself as a physicist, learning new tricks by looking at nature. Space, the whole galaxy, the whole universe. I know no better place to find new physics.
I'm really excited to be here today for two reasons. First of all, this is one of my favorite cities. My wife grew up here, and I spent a lot of times here at Christmases, holidays, and blues clubs, and many amazing restaurants around town. So I'm just glad to be back. But more importantly, I'm so excited to be here because of Eugene and everything you have done for this amazing field of science that I'm part of at NASA. What I'd like to do is really point to the fact, of course, that the way we look at this science today through the many telescopes that are out there as a result of the work that you have done, Gene, nature has become more beautiful, more complex, just like you said, but more beautiful. Look at this amazing image here by one of the recent NASA missions. You also pointed out, of course, that the way this started interacting with a coronal mass ejection as measured by stereo, but that these tails really indicate that there are fast winds. And these fast winds, of course, people really couldn't imagine, because what they thought about is that the sun would just like slowly bake off, and a really small kind of breeze would happen there. Oh no, that space between the planets is a lot more exciting, with a lot more science going on than anybody predicted. Of course, just a few years later, your prediction was confirmed with Mariner 2, that was outside of the bow shock of the Earth and saw the supersonic solar wind, just like you said, approximately the temperature that you had said, density was a little bit less perhaps than you said in your initial paper. If I ever write a paper that's accurate, I'll be really, really glad. But this is from Mariner 2. In addition to that, of course, what that spacecraft did and subsequent spacecraft, they also observed the magnetic field shape that was later in the same paper that you predicted, a magnetic field that we refer to as the Parker magnetic field. And so it's that observation that was also made. So really making this a huge home run, and really one of the biggest kind of discoveries, I believe, in solar and space physics, or heliophysics, as you pointed out. Once you have the solar wind, and you know its speed and its density, you have a guess about the magnetic field and the structure of the galaxy, which is another subject area that you focused on, the recognition that there's magnetic fields out there, and that this universe is not just gravitational, it's really magnetic, and there's important impacts that happen. Once you know the solar wind, you can guess how big that bubble is, that kind of space that is filled by the sun. We refer to it as the heliosphere, and only about 5 years ago did we cross through that boundary into our galactic environment, work that our friend Tom Kermici is sitting right here, and his colleagues on Voyager have done amazing work with. And basically, we're right now on the outside with one of these missions, we believe, looking at, for the first time, that galactic environment. Again, a magnetic galactic environment of the types that you have predicted, whereas the other Voyager is kind of still sneaking up on that boundary from the inside. Going back to our near-Earth environment, of course, what we have right now is these missions out there. We call them magnetosphere multiscale missions, and what they're observing is an important process that you talked about really early on. With SWEET, you talked about the merging of magnetic fields and the important interactions that would happen if these magnetic fields, in fact, coalesced and reconnected. We talk about that process as reconnection. Only just a couple years ago, or even this year, there are new science papers out there that talk about the first really in situ multi-point observations of these processes that are important, not just near Earth, where we observe them right in front of our door, but they're universal, because we observe these processes around astrophysical objects around other planets in many different places in the universe. And so that's another one of the seminal papers. But going back to the sun, you know, like who would have guessed how amazing the sun looks? Look through the kind of eyes of somebody who understands that there's magnetic fields there. You know, the corona, the atmosphere of the sun, of course, is heated to a temperature much higher than the surface of the sun because of processes we're still trying to learn about. You wrote a paper that basically talked about microscopic kind of nanoflare type of heating events that will be at the heart of that heating, the amazing structures that we see there. And there's a lot of evidence and papers that we see in the literature even today that basically point to the fact that this is much more likely than we ever would predict. But we want to go check. And that's really where kind of the culmination, I believe, of the research that we've been doing in this field in solar and heliospheric physics and heliophysics in general is, and that is about the solar probe mission. We want to go down there, take the challenge of going in the worst kind of thermal environment in the solar system, survive that because we built the machines robust enough to do that, measure the environment there and really prove and find what the kind of heating processes really are that in fact make the corona hot and accelerate the solar wind. Now, NASA has named about 20 spacecraft after distinguished researchers like Hubble, Chandrasekhar, and Fermi, all of them with Chicago ties, many others, about 20, not many. There's a lot more Nobel Prize winners than people that have been have spacecraft named after them, so about 20. However, NASA has never named a spacecraft after a researcher during their lifetime. Well, ladies and gentlemen, we're about to make history. It is my great honor, a few days before your 90th birthday, Gene, to announce that we're renaming the Solar Probe Plus spacecraft to be known from now on as the Parker Solar Probe. Congratulations. Thanks so much. Really appreciate it. Go ahead, Jim.
I wrote my speech down here, and I don't intend to reiterate what you've already heard plenty of, but I'm certainly greatly honored to be associated with such a heroic scientific space mission. By heroic, of course, I'm referring to the temperature, the thermal radiation from the sun, and the extreme measures developed to survive that radiation and collect scientific data should be fully appreciated. You've heard the design of the spacecraft in earlier lectures here, I'm sure, but it was not easy, and I thought I would run through the two main effects. For instance, the initial development of solar probe concept at JPL showed the extreme technical possibility of a spacecraft surviving an orbital plunge into 4 solar radii. Essentially, JPL went for broke. They designed a fabulous spacecraft, and the sunlight, and this is what grabs me, the sunlight is 3,000 times more intense at 4 solar radii as it is out here of Earth. It really is something amazing. Unfortunately, only very restricted instrumentation can survive because the spacecraft serves as a heat shield, and you do not dare poke anything out from behind that heat shield to make a measurement. So there's some exceptions to that, but you're very limited. The next go at the problem was Solar Probe Plus, as you all know, the Applied Physics Laboratory, designed for a slow approach inward to 9 solar radii, where the sun is only 570 times more intense than it is here at the orbit of Earth. And it is possible to operate a complement of instruments peeking out from behind the heat shield for an extended period of time. One of the drawbacks of the original solar probe was that it's all over in a few hours at the 4 solar radii. As a theoretician, I greatly admire the scientists and engineers whose patient efforts together converted the solar probe concept into a functioning reality ready to do battle with the solar elements as it divulges the secrets of the expanding corona. So, hooray for Solar Probe. Thank you.
Wow, just wow. I am Nikki Fox, and I am so honored to stand here today representing the Solar Probe team. And this isn't just the team that's building this particular mission, but I really feel it's the thousands and thousands of researchers who've poured their heart and soul into making this reality, this mission a reality over the last 60 years. Solar Probe is going to be the hottest, fastest mission. I like to call it the coolest, hottest mission under the sun. We are going to be moving at blistering temperatures. We are going to go right up into the corona. As you've heard of the revolutionary work of Dr. Parker from as far back as 1958, still we have not been able to answer these key questions. There's been so many NASA missions who've made tremendous advances. We've done so much with remote sensing. We've been inside the orbit of Mercury, and we've done amazing things. But until you actually go there and touch the sun, you really can't answer these questions. And these questions are so simple. Why is the corona hotter than the surface of the sun? That defies the laws of nature. It's like water flowing uphill. It shouldn't happen. Why in this region does the solar atmosphere suddenly get so energized that it escapes from the pull of the sun and bathes all of the planets? We have not been able to answer these questions without actually taking a probe into the sun. And we're going to be moving at blistering speeds. We will be moving at about 430,000 miles an hour. That's about 118 miles a second. Wouldn't you all enjoy your morning commute at that speed? We're going to be 7 times closer than any other mission has ever been. And we will repeatedly swoop through the corona making these measurements. So why has it taken us 60 years to be able to do it? Because honestly, the materials didn't exist to allow us to be able to do it. The very first thing we had to do is make a heat shield, and we love our heat shield. Our heat shield was developed using NASA research money. It was led by APL together with the Whiting School at Johns Hopkins and many other contributors who'd actually designed a carbon-carbon composite to be able to not just withstand the temperature, but also we're doing 24 orbits. So we actually go hot, then cold, then hot, then cold. And getting something that will withstand that kind of thing is really revolutionary. We also had to design new solar panels, keep them cool. They're kind of on like a shoulder joint, so they move in and out as we go close and further away from the sun. And we're so close to the sun that just the little fingertips poke out from those solar panels, and that generates enough solar energy for us to be able to operate the mission. Right now, the spacecraft is being built and tested, being put through a lot of rigorous testing to make sure we can withstand that environment. We're going into the corona. As you heard, the corona temperatures can get up to a couple of million degrees. We're not going quite that close, but still where we're going to will be at 2,500 degrees Fahrenheit. And yet our instruments that are tucked in the shadow behind our heat shield will be operating at about the temperature of this room, about room temperature. So we're building it, we're testing it. We have a couple of the instruments already integrated. By the end of the summer, most of them will be on. And it is my pleasure to be able to introduce you to representatives of our science team, our principal investigators from the payload. So in the order that you're sitting, I will introduce Justin Casper from the University of Michigan. He's also a Chicago alum, by the way. Stuart Bale from the University of Chicago, University of California, sorry. University of California in Berkeley, I've got Chicago on the mind. Dr. Dave McComas from Princeton University. Dr. Marco Velli from University of California, Los Angeles. And last but certainly not least, Dr. Russ Howard from the Naval Research Lab. And so together, using a variety of in situ and remote sensing, we will finally answer these questions. I also want to introduce one more person. I like to call him the man behind the curtain. He's our project manager that keeps us all going on schedule, on budget, and never lets us take a vacation. Andy Dreisman. So what's next for us? So I said we are building, testing, integrating the instruments, biting our fingernails. In the end of this year, we will actually move to Goddard, where we will do some final testing, including the kind of nerve-wracking thermal environment, where we make sure that everything's going to work in that environment. From there, we go down to Florida, and we launch on a Delta IV Heavy. And we also have a third stage, and that's because we need to be moving so fast so that we can kind of surf around. Now, many of you are used to hearing about gravity assists where we actually accelerate the probe. We are very generous. We are giving energy to Venus. We're actually using the Venus flybys to just trim and really precision of where we need to be to make to actually hit our solar orbital targets each time. Just 8 weeks after that, we will encounter the sun for the first time. We will do our first closest approach. Following that, we will do another 6 Venus flybys over the course of just under 7 years. So we kind of gradually get closer and closer and surf more and more gracefully in towards the sun until we're just under 4 million miles or 10 solar radii. Now, 4 million miles may not sound that close to you, but if the Earth and the sun were separated by 1 meter, we would be at 4 centimeters from the sun. So it's actually very, very close. In fact, so close that we'll be in a region that you yourselves may be able to see this summer. During a total solar eclipse, you are able to see the hazy corona around the sun. August 21st this year, the first time in 100 years, there'll be a total solar eclipse that is visible from the USA. So I do encourage you to go and see it. When you look up and you see the eclipse, solar probe's going to be right in there. Not only are we doing basic science, but we are also going to be providing critical information that will allow us to better forecast how our Earth's environment responds to the sun. We'll be doing critical advances that will enable us to better predict space weather. So for that reason, we're going to send Solar Probe into the corona, and we will finally touch the sun.
NASA's Parker Solar Probe mission is about to embark on a historic journey to our very own star, the Sun. Named for Dr. Eugene N. Parker, whose contributions have revolutionized our understanding of the Sun, Parker Solar Probe will usher in a new era of exploration. It's a mission of extremes. The spacecraft will plunge through the Sun's atmosphere, called the corona, and fly closer to the Sun's surface than any spacecraft in history. More than 7 times closer. The Sun's surface is hot, at temperatures exceeding 10,000 degrees Fahrenheit. But the real surprise is, its atmosphere is even hotter, 300 times hotter. Facing the corona's brutal heat and radiation conditions, Parker Solar Probe will finally provide answers to some of the most important questions about how our sun works. As Parker Solar Probe speeds around the sun making these measurements, it's moving at over 430,000 miles per hour. That's like traveling from New York to Tokyo in less than a minute. This mission is the culmination of 60 years' work by the best and brightest scientific and engineering minds. Today, our technology will let us achieve our dreams, to reveal the secrets of the corona and our sun, and to one day help better protect technology from the threats of space weather. In 2018, we will launch Parker Solar Probe, humanity's first mission to touch the sun.
Okay, I'm sure there's not a dry eye in the house of anyone who's actually associated with that mission. Okay, so it just remains for me to say that to Dr. Parker that we are going to be flying a chip on the spacecraft. We're going to put some photographs of you and your seminal paper from 1958. We're also going to have it on a mounting plate, and we would like to invite you to write whatever inscription you would like us to put on that plate and send to the sun. And then the final thing I have to do is it's my great honor on behalf of the whole Solar Probe team to present you with the very first scale model of Parker Solar Probe.
Well, as I said, I'm greatly honored to be associated with this heroic scientific mission. And I was just examining it here. I guess I need some instruction as to what all the things are here. So thank you very much.
Now we'll take a few questions from the audience and from social media. Please raise your hands and our staff will come to you with a microphone. Once you have the microphone, please identify yourself and your affiliation and then ask your question. Yes, a question from this gentleman in the front. Yes, you need a microphone. And identify yourself. No one here knows you.
My name is Eric Isaacs. Can you please say a little bit more about the kinds of instruments you actually have? And maybe this addresses Gene's question about what's on the model. But what are the instruments you have, and what are your wildest dreams about what you hope to find?
Okay, Nicola, let's.
Yes, we have a full complement of instruments. So as you've already met the PIs, but we have the sort of bulk plasma, the bread and butter of the solar wind, if you will. We have a couple of instruments that are going to be measuring what's coming out radially from the sun, and we have instruments positioned in different locations, so whatever angle it comes out as, we've got it. We have a full suite of magnetic, so here's the magnetic instruments on the back here, the electric fields on the front, so we can measure plasma waves. We have a high energetic particle suite to get the stuff that comes with the flares and the shocks. And last but not least, we have a white light imager called Whisper that is going to be taking pictures of the structures that we're about to fly through. So it will help us put into context what we're seeing. Wildest dreams, I want to go and explain Parker's paper. That's what I want to do.
Great. Thank you, Nicola. Let's see, we have another question right there.
Hi, Charlie Wojciechowski from NBC5 in Chicago. Why is it important to send this into the sun? Why is it important to touch the face of the sun rather than just brush closely by it and preserve the satellite?
So we will brush closely by it. We're obviously not going to go right up and touch it, but if you imagine, you can learn so much from looking out the window. You can see the sun is shining, you can see the birds are singing, but until you actually go out, you have no idea quite how hot it is out there or how windy it is or what the conditions are like. So I think we've really come as far as we can with looking at things, and it's now time to go up and pay it a visit.
Now we'll take a question from social media. We have a tweet.
We do have a tweet. We have a question from Joel, who would like to know why we are only going to 4 million miles. Is there a limit on the heat on the orbit? What are the parameters?
So there's a couple of things. I mean, obviously, it's designed, the heat shield and various things are designed to work at the 4 million miles. The reason we can't go any closer is after our 7th Venus flyby, our furthest point away from the sun is actually now inside the Venus orbit. So we can no longer use it to trim the orbit and move closer. So we're going to go to 9.8 solar radii is pretty good. I'll take that.
Okay, thank you all. Now, before we close, I believe that NASA they haven't done very much. So they have a final special recognition to present to Eugene. Please welcome back Thomas Zurbuchen.
Kleenex up here. You're good, you're good. Before I do that, I just want to quickly tell you two of my Parker stories, just so I know how I got to know him. First conference I ever went to, I was in Switzerland, and like people there, well, men there, I was in the military, and I got time off from the military to come to the first conference, and so I walked in, was on the train the whole night to Germany, where that conference was, and I walked in the door and I sat down, and so I didn't know who was there. Of course, I had read all your papers, right? And so I sat there in the conference, and some guy gave a talk, and you jumped to your feet and asked a question. Everything was quiet, like momentarily, like because you got up there. And like, he asked a really good question, were really nice. He struggled. He really lost his footing. You know, you're preeminent person in that field. You don't want to get hard questions from Gene if you can help it. But anyway, so he did a good job. You were really nice to him. I asked everybody, who is this guy? Why is everybody stopping? That's Eugene Parker. So for me, that's how I met you. You, of course, wouldn't know. You saw my back from where you were sitting. I'll give you another story, and that is when I invited you to a seminar to the University of Michigan. I thought it was really important that students saw the kind of leaders that you are, and I basically asked you, you were hanging out with the students, very generous with your time, just like you were in that first conference when we later met. But the time you spent there, I basically asked you, how do I introduce you, Gene? You know, like I could, talk about the kind of things we talk about here. How do I introduce you? And you basically said, well, how about you introduce me like this? So I did my grad school, couldn't find a job, went to Utah because that's the only people who actually offered me one. And due to a friend, got back to Chicago, wrote papers I couldn't get published. Due to another friend, I finally got them published. And then the rest was pretty good. See what I liked about this? I said, why would you want me to introduce you that way? And he basically said, well, these students need to know that even if you're successful, it's going to be hard from time to time. And many of the most important science discoveries that we have are a little bit controversial at the beginning, or very, very, very controversial, like you have. So those are kind of two of my anecdotes I want to talk about. And for the next thing, I'm going to ask you, Steve Clark, you're the Division Director of Heliophysics, to come up. What I want to do first is talk to you about the Distinguished Public Service Medal of NASA, and it's the highest form of recognition awarded by NASA to an individual who is not a government employee. It's awarded based on the merit of that person, on the excellence towards NASA and the nation, and it's that medal that we'd like to give to you now. Let's come here. So what I'm going to do is read the dedication, which is signed, of course, by the administrator. This is only the administrator can give that medal, and it is for a lifetime of extraordinary scientific achievement and outstanding leadership in space science and NASA's space program. Gene, it's an honor to give you that medal. Congratulations.
Thank you, Tom. That's a pleasure.
Okay. Thank you.
What a wonderful morning. Thank you, everyone watching across the country, and to all of you who have joined us here at the University of Chicago. There will be a short media question and answer, so media, you are not allowed to leave the room. Please remain. Everyone else, please join us in the atrium for a reception and demonstrations. Thank you very much, and thank you, Gene.